Well, our objective is to find the solution of equation cos of x minus x equal to 0, which is to get the value of x at which this curve, this function crosses x-axis. Our objective is to implement Newton-Raphson's method. So I begin with the iteration number. This is just to keep a record. Then Newton-Raphson method begins with the x in old value of x, initial guess. Then we have to compute the function value. So I write here, okay, this is the computation of f of x. These are just the titles, right? And this demonstration, I am explaining the whole algorithm step by step. The way I am moving from left to right in Microsoft Excel sheet, this is the sequence of calculation that you will adopt in while writing your program. Then we compute the derivative of x at the old point. Well, let's shift the title to x old so that it is the function evaluation at old point. Then we say f prime of x old. Fp means f prime of x old. And then new value of x will be computed. So the 4-step process, right? And then the error check. So iteration first, right? Starting from 0. So for this problem, let me set a value. As we know from cos of x minus x, cos of x is going to oscillate between -1 and 1. So, well, for solution domain, it is in pi. Okay. So x values, let's suggest say 0.5 value, right? Then f of x old. So I write here in this cell, it is equal to cos of x value. I pick the value of x from the cell selection, cos of x. So x value, x old value is at B2 minus x value again from B2, right? This is also case insensitive, right? So this has been computed. Now the derivative of this function is required just for making a record. The derivative of this function. Well, the earlier function was, we have been calling it f of x, and we require f prime of x. So it is f prime of x, okay, fp of x. Fp of x would be minus times sine of x and minus 1. Okay. So we compute the value equal to minus sine of x old value minus 1. Now the computation of new value. Let's expand the cells a bit so that view is much clearer. So step-by-step calculation, right? X new is equal to x old value minus f prime of x, no, sorry, f of x old divided by the f prime of x value, right? Values have been picked from their respective cells. So we have got a new value from the algorithm. Starting from x old value, we computed f of x old function value, then the derivative at that point, then the new value from Newton-Raphson's approximation, and then the error calculation, which let's define absolute of the new value minus the old value. So this is the end of first iteration, right? Now the next step, since the error is not very much small, is not small, let's perform the other iteration. So here we will have the iteration number. This is not really involved in the calculation. The first column, it is just for number checking, right? Manually we are checking it. Now the X value should be updated as the new value. Update the value. And then we have to repeat the rest of the calculations. So for that case, I will select these cells and I drag it down to repeat the next iteration. So you may watch that the error has been reduced to 2 decimal places, right? And now let's repeat the whole story. And behold, for a moment, Newton-Raphson's method. Within 3 iterations, it has converged to 10 raised to the power minus 10. Right? In Microsoft Excel, I have not stored the values in variables. I have shown the values as such. So this is here. Right? So that is the algorithm. Let's quickly develop a FORTRAN program for it. Are you ready? Waiting for this really moment? But by the way, let's change this one. Let's change the initial guess, initial approximation. Let me set it 1. Right? So all the calculations have been performed by Microsoft Excel again. Let's give it a vague guess, say 10. So it is diverging. Here the error is diverging. So we have to explore the method from the mathematics point of view to realize the limitations and effectiveness of the method. Under what condition it is going to perform, under what condition it is not going to perform. But let's see what it is going to do with 50. With 50, the answers are converging, right? So it is not just a matter that you are looking for a large value. Let me take another big guess, minus 50. It has converged. So we have to look for the properties of function in question for which we are going to solve its behavior so that our selection of a numerical method is intelligent. So quickly, let's develop the FORTRAN program. Because I am excited to show you the power of FORTRAN with the power of FORTRAN as well. So program Newton-Raphson algorithm, right? Newton-Raphson algorithm, and there will be an end program in our algo, and we require the function. So I define function f of x. And for this problem, real x, real f, and here comes the function definition. F is equal to cos of x minus x. And here comes the return statement. And then the statement of end function f. Let's define another function for defining the derivatives. So as I said, f prime of x, right? So real x, real f prime of x, right? And the f prime calculation is equal to minus times sine of x minus 1, and the return statement and end function, right? Function f prime. Okay, that's nice. And now let's populate the main program. Okay. So now the whole screen is being shared. But what I have done, I have defined a function for f of x, which is cos of x minus x, right? And the next thing I have defined as f prime of x, which is minus sine of x minus 1. So I have just defined two functions. And this was the right time to inform me about the error of screen share. Yes, it has been shared. So let's save the program in this present form, where we have only the definition of functions, function and its derivative. So NR FORTRAN file, NR algorithm dot for. Okay. So the main program, implicit none. I will define real x old x new error, right? And I must have integers, say I, and maximum number of iterations, right? Okay, so let's define a convergence value where we should stop. So I define epsilon, right? Epsilon EPS. So EPS value is defined 1 10 to the power minus 4, up to 4 decimal places. Okay, so here goes the algorithm. I start with the initial approximation, x old, say 0.5. Then I require the value of function, so I can call it. So I write Newton-Raphson equation. Newton-Raphson's equation. So here it goes. X new is equal to x old minus f of x old divided by f prime of x old, right? See how naturally and clearly it is following the sequence of the algorithm, right? The language is quite natural, the way we write on piece of paper and the way we are programming it. And then we compute the error. So error is equal to from absolute function x new minus x old, right? And then we have to update it, right? So I write here if condition, if the error is less than or equal to epsilon naught, then go somewhere, right? So let's write in the form of a while structure, right? In while structure or do loop structure. Let's prefer the do loop structure. Do I varies from, okay, all do I varies from 1 up to 1000, right? So I is the iteration number. And right here, if the error is less than or epsilon naught, less or equal to epsilon naught, then break this loop, right? So to break the loop in FORTRAN 77, we have to write a statement. Go to 100 and else it should keep on performing the calculation. And I have written in the slightly newer style of FORTRAN. Let's add indent to that. Okay. So far, we have not printed any kind of answers. Any answers? Where is the end program statement? It's way down. So here, I write here a print statement, program ended after iterations. So how many iterations after it has ended? So it is the I iteration. So far it is correct, but let's add some print statements so that everything appears as we have seen in the Excel sheet. So let's print some values. So I print values with some format. I will print value of I, iteration number. I print the value of X old. I will print the value of X new, and I will print the value of error. Right? Is it logical? Right. To me, it's very logical. I write one X format, then I write I 4, right? Maximum iteration, so that it can accommodate 1000. Then I leave 2 blank spaces, and for writing 3 real numbers, okay, 3 real numbers, let's okay, write the format E okay, F of 7.4, since we have written the convergence criteria up to 4 decimal places, right? 2 times this one, and then 2x, and write the E format 9. Right? So 2 real numbers with the F format and 1 real number which is error in the exponential notation. Right? To make a title for it, okay, this parenthesis seems to be extra. To write a print title, write outside loop a title statement. So for that, replace all the things with a, sorry, all F7. So 7 positions, and here a 9 position, right? Okay, that's it. I have added print statements to give you the titles. Okay, we have functions, and we are calling these fx function and f prime of x function the Newton-Raphson's calculation. It begins with the x old value, x new value is computed, error is computed, and is printed. And if the error is less than epsilon, right, go to means break the loop, but else we have not provided a statement of updating the approximation, right? So it should be here, else update the initial guess or approximation. So I would say x old equal to x new, right? So this is the program. Let's save it and see it's working. Behold, we are very close to enjoy our success. Newton-Raphson's algorithm dot for minus so Newton-Raphson's algorithm dot exe. Okay. Oh, with the implicit none, f, p, and f have not been identified in the main program. So we must have their identification, real f and p. Right. One more time. My students are very patient. Right. I'm very lucky to have such a nice class. So we have the successful compilation of the program. And here, great moment in your life, seeing the Newton-Raphson's method working in front of you, right? After centuries after the Newton's work, transformed by Rizwan Ahmed. So titles have not been printed in a nice way. However, the errors have been converged, right? After 3 iterations, the answers have been returned. So very nice, very nice. Even though we didn't wish for that one, but somehow very interesting titles have been printed. Let's correct that. Where is the error? So in the print statement, okay, the titles I wish to print, but it looks nice without the real title. Sometimes the errors give you happiness. This is for the first time that the error has given us happiness. That was really great moment. So actually I was printing characters and I have provided real or integer variables. So this is something that we have to control, and we have also to keep a check. Well, we are working in the within the execution limits of FORTRAN. We are well before the 72 column. So let's correct even that smiling error as well. And also let's change the initial approximation to see a bit more iteration. We have seen that at -50 it was converged. Let's improve the value to well, increase the convergence value, right? Error bound is further reduced, more accurate result, 10 raised to the power -6. So if the problem is in meters, we are looking for micrometer accuracy in numbers, right? But we cannot go beyond the -7 because we are using the real arithmetic, right? Decimal places. EPS has been updated. Well, I didn't wish to record that sound in my program, but it's there. Newton-Raphson algorithm. Okay, in 8 iteration, the answer has converged, right? So 4 decimal places were written over there, right? Okay, so there was some problem with the first XOR. With the format was not sufficient to print that one. Okay, so we have successfully implemented the Newton-Raphson's algorithm. So this can be more generalized in a function form, and it can call external functions as f of x and f of p.